Bright Tuty. Every student matters.
Hello students, my name is Sanjay Jain. In today's lecture we will revisit the irrational numbers, right? Till now in the lectures on real numbers we have covered Euclid's lemma, right? Euclid's lemma and Euclid's division algorithm. Apart from that, we used division algorithm to calculate HCF and LCM. We used division algorithm for HCF, and then after that we did fundamental theorem of arithmetic, in which we talked about factors of a number, right? And we also discussed that every composite number can be factorized into prime factors, right? And that factorization is unique apart from the order in which it is written, right? In this particular lecture we will discuss about irrational numbers. Okay, so what do you know about real numbers? Real numbers are made up of rational numbers plus irrational numbers. So if I write all the rational numbers and all the irrational numbers, right, so that will be all the real numbers. What are rational numbers? Rational numbers are either they will terminate, terminating type. If they do not terminate, non-terminating, then they will repeat after a certain period of time, right? After certain digits. So non-terminating, repeating. If I have to give an example, rational numbers, let us say 1.2, it is a rational number. So it terminated after a time, right? Now if it doesn't terminate, it will start repeating. Let us say 1.23, 23, 23 and so on. So we write such numbers like this by putting a bar on the repeating digits. Okay, so this is 1.23. One more definition is there for rational numbers, that these are the numbers which can be written in P by Q form. Let us say I have taken P and Q as any integers, and if I can write it in P by Q form where Q is not equal to 0, right, then that number is rational number. And you will see in the upcoming exercises that such numbers will either terminate after certain digits or they will be of non-terminating and repeating type, right? Irrational numbers are such numbers which do not terminate, non-terminating and non-repeating. As the name suggests, irrational, they do not follow any pattern, right? So let me write such number 1.235, let us say 236, 237 and so on. Okay, it doesn't terminate anywhere and it doesn't repeat itself. The digits after the decimal sign will not repeat. Okay, so such numbers are irrational numbers. They cannot be written in P by Q form where Q is not equal to 0. Also there are some more examples like root 2, square root of 2, right, square root of 3. And you should notice that square root of 4 is not an irrational number. It is a rational number because root of 4 is 2. So if under the square root sign there is some perfect square, okay, it will not be an irrational number. Apart from that, if there is anything which is not a perfect square, so this will be an irrational number. And if there is any prime inside, it will be an irrational number. Okay, so these are some of the examples of irrational numbers. Now in this chapter we will also prove, we will give a proof by contradiction method that root 2, root 3, 2 plus root 3, these are irrational numbers, right? Before that, let's do a small theorem using fundamental theorem of arithmetic. Okay, what does fundamental theorem of arithmetic say? That every number can be factorized in its prime factors, right? Let us say a is a positive integer, right? And using the fundamental theorem of arithmetic, I can write A in factors of its prime, right? In prime factorization form, right? Let us say these are up to Pn. Okay, these P1, P2, P3 are primes. Okay, so if I write A in prime factorization form, so this will be the prime factorization form. Now what I am saying here is, if P is prime, right, and P divides A square, then P will also divide A, right? If I have to write it mathematically, then I will say P divides A square will imply that P divides A. Okay, this vertical line is for P divides A square, then this implies that P divides A. Why I am saying this is because I have written the prime factorization form of A here, right? If I have to write A square, then I will write it as A into A, so it can be written as P1 into P2 into P3 into up to Pn, and then once again P1 into P2 into P3 into up to Pn. Okay, let us say we have got a prime P which divides A square. Let us say if P divides A square, right? If P divides A square, then P has to be a factor of A square, right? Then P is a factor of A square, so it should be there in the prime factorization of A square, which is this, right? So P can be one of these only. P can be one of P1, P2 up to Pn, right? Apart from these P1, P2, Pn, there is no other prime factor of A square, right? This is written 2 times. This bracket is written 2 times. Both the brackets consist of P1 into P2 into P3 up to Pn, right? So if something has to be a factor of A square, it has to be from these 2 brackets. Okay, so P can take, let us say, any value out of these. Okay, apart from these there is no other value that P can take. If P is P3, okay, if the prime that we are talking about is P3, right, it is present twice in A square, right? For that matter, any prime that divides A square is present twice, right? It is present in both the brackets. So I can say if P divides A square, P is a factor of A square, so P can be one of these, hence P is also a factor of A, right? So I can say P divides A, right? I hope I have explained it enough that if there is a prime factor P which divides A square, right? So that P can be any one of P1, P2, P3 up to Pn. There is no other option for P, right? If it is any one of P1, P2, P3 up to Pn, then it will be present 2 times in this product of A square, right? In this expansion of A square, you can see it is clearly present 2 times. Okay, so and this is expansion of A, this is also expansion of A. So A square is A into A. So if P has to be present, it has to be present in A also. If P divides A square, then it essentially divides A also. So I can say if P divides A square, if P divides A square, it will imply that P divides A. Okay, and we will use this fact in the upcoming exercise, so you should be really clear about this concept.